2 where we understand what a logarithm is, and we've worked with evaluating them and graphing them. We want to look at some properties about combining them and breaking them apart and evaluating them further, right? So the first thing we look at is, what if they give me a log? Up until this point, every problem that we've had that was a logarithm, we switched to exponential form and solved it. But what if they give me a log that I can't switch to exponential form and solve? I mean, if we were to switch this to its exponential form, that would be 2 to the x equals 6. If I rewrite that as 2 to the x equals 6, I can't get my bases the same. There's no way to rewrite 2 and 6 with a common base so then I could set my exponents equal to each other. And that's the first time we've encountered something like that. So when that is the case, I'm going to need a different way of solving it, and what I want to use is the change of base formula. On my calculator, I have a base 10 button and I have a base E button, and that's it. I don't have a base 2 button on my calculator. And so it would be nice if I could change my base over to something that is on my calculator that then I could evaluate. Or to change it over to a different base that would work with the numbers that I'm working with so that I could evaluate it by hand. And so I'm going to use my change of base formula, which is on page 240. The change of base formula says if you're trying to find the log base a of x, you can rewrite that as the log of x over the log of a using any base that you want, as long as you use the same base top and bottom. So if you have the log base a of x, you can rewrite that as the log of x over the log of a with any base you want, as long as you use the same base top and bottom. So the two most logical things for us to choose would be the two buttons that are on our calculator, right? Like maybe we would write it with a base of 10. So if we rewrote this with a base of 10, that would be the log of x over the log of a, because when we write no base, we assume 10. Or log base e, right, ln? So we could write that as ln x over ln a. So let's see that with this example that we just had. If we had log base 2 of 6 and I wanted to write that with common logarithms, then I could go through and I could say, all right, that'd be the log of 6 over the log of 2. So that's a log base 10, and then I could evaluate that on my calculator, right? The other way that I could write that would be with natural logs. And I want you to see that it doesn't matter which way you use it. So grab your graphing calculator if you would. And let's throw this one in, log 6 over log 2. Log 6 over log 2. So again, I'm just using my log button over here because that's my common log, log base 10. So if we do log 6 over log 2, I'm going to get 2.585 if I'm rounding that to 3 decimal places. All right. The other way that we said that we could rewrite this is with the natural log, right? So if I wrote this with the natural log, in this case I want to use ln, then I'm going to say ln 6 over ln 2. So again, I can use any base that I want to, as long as it's the same, and I'm going to get the same answer either way. Now, if you have the new operating system for your calculator, you can avoid change of base formula altogether, because you got a handy dandy new button on your calculator that did not come originally on the calculator. If you go to alpha F2, see number 5 down there? That is a happy thing. Choose number 5. You can type in any base that you want and any number that you want, and it basically does the change of base formula for you. it's doing the same thing that we just did by hand. It's just you type it in that way, and it uses change of base to evaluate. Okay? So if you don't have the new operating system, if you have an 84, you surely can get it from me. If you have an 83, you cannot, but you can use change of base formula to evaluate those just as well. Okay? So just a reminder of those things that we did. We rewrote the log base 2 of 6 with a common log using change of base formula. We also rewrote it with a natural log using change of base formula and got the same answer. We also saw that if you have that new operating system, that you have a happy little log button. And so when we chose that log button, then we were able to type in whatever base and whatever value that we wanted and got the same answer. Okay? And that also works in graphing, by the way. So like if you were trying to do something like we were with number 57 on the homework last night, where you had to, they said, check your answer with a graph. They had not taught us change of base yet. So, how am I supposed to know how to put that in my calculator? They get a little bit ahead of themselves sometimes. So you would have had to have switched that to exponential form and played around with it a little bit to do that. But now we have a fast, easy way that we could go to y equals and type that in exactly as it is, either with change of base or with this button if you have that. All right, so then they give me some properties of logarithms over on page 241 that will also be big shortcuts for us. All right, the first one says if you have the log of two things that are being multiplied, you can break that into two separate logarithms that are being added. Now, remember logs and exponentials are inverses of each other, right? When you're working with exponents, when your bases are the same and you're multiplying, what do you do to your exponents? Add them, right? So it's the same kind of idea here, right? When my base is the same and I'm multiplying, then I'm going to add. So that might help me to remember that, okay? I also can go the opposite way with that, where if I have two logs that are being added and their bases are the same, then I can combine that into one single logarithm where those values are being multiplied. All right, look at the next one. If I have the log base a of u divided by b, that's the log base a of u minus the log base a of v. So in exponents, when your bases are the same and you're dividing, what do you do with your exponents? Subtract them, exactly. So when your base is the same and you're dividing, you can subtract. That'll be a way to help you remember that. And again, the opposite way is true. If you have two separate logs that are being subtracted and they have the same base, you can combine them into one single logarithm where the values are being divided. All right? Then we have a property that says if I have the log base a of u to the n, where n is an exponent, you can pull that exponent out in front and multiply it by that logarithm. So that would be a way to clear out an exponent. So that exponent can get pulled out in front and multiplied by your logarithm. All right? Now, the three properties that you see over here are not additional properties. They're the same three properties, but instead of being written with a log base a, they're being written as a log base e, or an ln. All right? So we could go through and we could say, if we put an e in the place of that a right there, then that would be ln uv is equal to, put an e in the place of each of these guys, and that would be ln u plus ln b. So it's the same three properties. When you're dividing, you subtract, and when you have an exponent, you can pull out in front and multiply by it. Okay? So look at example 4. Example 4 says, use the properties of logarithms to verify that negative ln 1/2 is equal to negative ln 2 to the negative 1. All right, so let's start with this guy over here. What can we do with that negative according to the properties we just learned? If you have a negative out in front of your logarithm, what can you do with it? Put it in the exponent, all right? So that would give us ln 1/2 to the negative 1. What's 1/2 to the negative 1? Positive 2, right, because you have a negative exponent, then basically you have to move across the division bar to get rid of that, or flip that fraction. All right, let's work on the other side. On the other side, I also have a negative out in front here. So if we do that same thing, if we make that negative that was out in front an exponent instead, I would have ln 2 to the negative 1 to the negative 1. When you have a power raised to a power, what do? Multiply, right. So negative 1 times negative 1 is going to give me positive 1 and I got ln 2. Okay? So we verified that both sides of that are the same thing. We've been able to simplify them down to the same quantity. All right, example 5 asked us to use the properties of logarithms to expand the log base 10 of 5x to the third y. So sometimes I have a log that's really complicated to work with it as it is. It'd be nice if I could break it apart into separate pieces, and then I might be able to do something with it. And so that's what they're asking me to do here. I've got 1, 2, 3 things that are being multiplied. So I want to use this multiplication rule up here to be able to break this apart into separate logarithms. So the multiplication rule had said that if I had log of a value that was being multiplied, I could break that into 2 separate logs, or in this case 3 separate logs that were being added. So we had 5 times x cubed times y, so we've broken that into the log of 5, the log of x cubed, the log of y. All right, what else could we do to that? Any other way that we could break that apart or simplify it? Okay, we can take that exponent of 3 and, right, we can put it out in front of the log. Now, do I put it in front of this log or do I put it out in front of the whole thing? Just that log, right. Because the exponent was only on the x cubed. If they had given me something like 5x cubed y in parentheses where that whole quantity was being raised to an exponent, then yes, that exponent would go out in front of the whole thing and I'd put, brackets around the whole thing or something like that. But because that cube was with the x only, it didn't apply to the 5 or the y, then it's only going to apply to this log. It won't apply to the log that has the 5 or the y. Good. All right, example 6, it says use the properties of logarithms. And this time we want to go the opposite way. This time, instead of expanding it, we want to condense it down. And we actually seem to do that a lot more often, where we take logs that might be harder to evaluate, and we combine them into and simplify them into something that might be easier to evaluate. I definitely could evaluate these 2 logs that are here. It wouldn't be obvious, and I'd have to work 2 separate problems and then combine those answers. So why not try to combine first and just work 1 problem, all right? So if I have 2 logs that have a common base and they're being added, what can I do? Multiply, right. So we would multiply the 2 times 32 and get 64. So what's the log base 4 of 64? 4, right, because we're saying 4 to the what equals 64, and that would just give us 3, right? 4 times 4 is 16, times 4 is 64. Now, again, if I had evaluated these, I could have. I mean, if we had said 4 to the what is equal to 2, that would have been 1/2. And if we had said 4 to the what is equal to 32, that would have been a little trickier. I would have had to say 4 is 2 squared and 32 is 2 to the 5th, and then, set my exponents equal to each other, and I would have ended up with x is equal to 2.5. So if I had 2.5 here and 1/2 here, and I put them together, I'd get 3. So I still could do this that way, but this is so much simpler, right? Anytime you can simplify a problem before you evaluate it, I want to go that route. All right, example 7, same idea. They ask us to condense the logarithmic expression, all right? So if I'm going to condense this, talk to me about some things we could do. I want to combine it into one single logarithm. Okay, so we've got log x, and we could raise it to a power. Where are we going to get the power from? The 1/2, right, the value that's out in front. So we're using this property kind of in reverse. If you've got a power out in front, then you can make it an exponent. All right, what else? How else could I condense that or simplify it?
opposite of multiplication?
Okay, so if I have that multiplication rule that says that if I can multiply, I'm going to break that into two separate things that are being added, then absolutely we could do the opposite of that, where if we have two things that are being added, we could combine them by multiplying. Before I combine these by multiplying, we've simplified this one. Is there a way to simplify this one? Okay, let's make the 3 an exponent to get it out of the way. And then absolutely we could combine them by multiplying as you mentioned. And you could leave this as x to the 1/2, or you could write it as square root of x, either one.